Okay, we're going to take a look at the MOS transistor and examine its output conductance under various different scenarios. We're going to look at its behavior as VDS varies. We're going to look at its behavior as the temperature varies, as process varies, and finally we're going to look at device scaling, which is effectively the ability of the designer to change the transistors W and L. So let's start a new schematic. But first of all, we'll go up here into the Tools menu, Control Panel, and just make a couple of settings adjustments. Go into the netlist options here and make sure that the default devices box here is deselected. Then go into the symbol and library search paths and make sure you've put in the search path to enable the simulator to find all your symbols and models. As you can see, mine are already configured here, but you can put in whatever path you want here and here depending on where you've put your various symbols and models. And about the only other adjustment I would recommend making at this time is in the drafting options, change the transistor, change the text size down to maybe text size 14 or maybe even size 12. Oh yes, and also turn off automatically scroll the view. That can be quite an annoying feature. Click OK. Go up here to Components. Go into your Custom Symbols and Models folder. And there you should find NMOS1, which is a 3-terminal transistor, and NMOS2. Select the NMOS2, 4-terminal transistor. Place it on your schematic. Go back up to Component. This time go into the LTspice symbol folder, scroll across to the voltage source and place one for the gate of the transistor and one for the drain. If you wish, you can change the name of these voltage sources to something like VGS and VDS. Also change the default voltages. I'm going to set VGS to 1.6 volts as a default and VDS as 5 volts as a default. Then wire up. And don't forget, of course, with any of these SPICE simulations that you must place a ground symbol somewhere on your schematic. All SPICE simulators require it. They simply won't run, or they certainly won't give you accurate results without the ground symbol. Now the only thing that's left to do now is to put some names on the wires or the nets. So we use label net tool. I'll call this wire D for drain, and this one here, just right clicking on this, G for gate. I would now want to change the device, some of the properties of the transistor. So I hover over the transistor, I hit Control, right click. You can see the default values for W and L are 10 micron over 1 micron. Change the 10 micron to 2, and then double click the SPICE model, the W and the L. We'd like to see those on the schematic, so that would be important for later on. And now we need to tell SPICE what we want it to do. So we go up here to this tool called SPICE Directive. We need to tell SPICE where our transistor models are. So we type in .lib, place that somewhere on the schematic. Then go back, hover over it, right click, browse, and browse to wherever it is that you've placed your custom symbols and models. In my case, I've placed them on the desktop in a folder called Inbox. You can put them wherever you wish. I'm going to select this one here, which is the BSIM P8U tip.lib, which stands for BSIM models, 0.8 micron, and it's the typical values. Select that, click OK. It appears on my schematic. I'm now going to put a simple dot op on the schematic, which tells the simulator to do a very simple operating point analysis on the circuit. So I'm just going to go up here to run, and everything looks to be working okay. We can see on the drain voltage here we have 5 volts, on the gate we have 1.6 volts, and the drain current is just a little over 41 microamps. That looks good. Now, the first simulation that we're going to do is just to do a DC sweep of the VDS. In other words, we're going to change the voltage from here from 0 up to some higher voltage, say 4 volts, and see how the transistor behaves in that situation. So we go up to Edit, Spice Analysis, we select the DC Sweep tab, and our primary sweep parameter is going to be VDS. So we type in VDS here, linear. We're going to sweep from 0 to 4 volts in steps of 0.001. Place that on the schematic. Hit run. Hover over the drain terminal on the MOSFET because we want to measure the current. And that looks okay. If we want to find out where VDSAT for this transistor is, there's no simple way to do it, but a relatively simple way to get an indication, an observational measurement, is to right click on your mouse, go down to this drawing tool, left click on line, and draw a line starting from the extreme right hand side of your plot. Left click there, stretch it over your drain curve, hit escape, and that allows you to see at roughly what point the transistor's curve starts to diverge significantly away from the straight line, which effectively represents the behavior over here in the saturation region. You can actually see it's starting to transition during this region here from saturation over here to the right to non-saturation down here to the left. And here's our transition region here. You can see a lot of this is happening in this region here, which is roughly in the vicinity of 0.8 of a volt. It's not a precise way of measuring VDSAT. The theory tells us VDSAT occurs at exactly VGS minus V threshold, but as you can see, it's impossible to pinpoint exactly when you can say you're right at the edge or the transition between saturation and non-saturation. So the best we can achieve with a simple analysis like this is just that straight line there, and we can see that it's happening in this region here, roughly in line with what we expect. VGS in our instance is 1.6. We know the threshold voltage is around 0.8, so we expect the transition between saturation and non-saturation to occur at around 0.8, and that in fact appears to be the case. It's not a precise measurement, but it gives us a rough indication. In another video I'll show you another more repeatable technique for doing this. Supposing we'd like to see how that simulation would behave if we had more than one sweep on VGS. Well, that's easily achieved. We just go up here to Edit, Spice Analysis. We select this tab here, Second Source, and so in this instance we're going to do 3 sweeps of the drain current, but at 3 different values of VGS. So we type in VGS here, and we're going to sweep from 1.2 volts to 2 volts in steps of 0.4. You can see that that secondary sweep or second source has appeared here in the text of the directive. Let's see what that looks like. So now we have a family of curves, this one representing a VGS of 1.2. I'll just delete that line there. This one representing a VGS of 1.6, and this one representing a VGS of 2 volts. If we would like to measure the R out, or the output conductance on any one of those, all we simply have to do is measure the slope of that line. So for instance, if we wanted to measure the R out at 1.6 volts, which would be the blue curve here, we go up here and hover over the ID label. We right click. We can see here attach cursor. It's at the default is none, but we're going to attach two cursors because we want to measure slope. At the moment, the two cursors are here and here, first and second. They're attached to VGS equal to 1.2. So I just select this one here. If I hit the up arrow, the up cursor control, it jumps that up to the blue plot, and then I select this one here, hit the up arrow cursor control, and that jumps us up there. Now you want to measure far away from this edge of saturation point here, or this transition region here. So I suggest you measure up around 3.6. So cursor 1 and 2 are going to tell you what the slope is between those two cursors there. You can see the slope here is roughly 1 e to the minus 6. And that gives you an R out, which is 1 over the slope, because remember this slope represents I over V, which is output conductance. If we want to know what the R out is simply equal to 1 over output conductance. And that's going to be approximately 1 megohm. Okay, let's get rid of that. Go back to our schematic. Now, if we want to know what the effective temperature is on this circuit, let's get rid of the secondary sweep here because we don't want too many different variables going on at the same time. I just hover over this and right click. Delete our second source. So that's gone off the schematic now. Put in a dot temp command and instruct the simulator to do 3 simulations, three curves at minus 40, 25 and 100. Let's see what that looks like. And so this time we've got a family of curves again, but instead of representing 3 different values of VGS, we've got a single value of VGS, 1.6, and what we have is 3 different temperatures. So how do we know which one is which? We go up here to Tools, Color Preferences, select the waveform, and you'll see V1, which represents the minus 40, because that in fact is the first one that we asked the simulator to produce. So V1, which represents minus 40, is the green one. So if that's minus 40, this is pretty much definite that this is going to be 25 and this is going to be the 100. You can check that out yourselves. And so if you just measure the slope of each of those at say 3.6, make sure you measure in the same point for each of them. Don't measure the slope of this one here and this one over here and this one over here. Measure them at the same point and just compare them. Now the next one, we'll get rid of that. That's temperature. The next one is the trickiest one. The next one is measuring or observing the behavior of the transistor for different process corners. And what we mean by that is you're going to have normal process variations, and one of the parameters we're particularly interested in is the threshold voltage. And it will typically vary from around 0.7 for the minimum model representing the process to around 0.8 for the typical model and around 0.9 for the maximum model. They're just ballpark figures. So what we need to do is we need 3 models now, not just a typical model, but we need a model for the min and the max of the process. So let's have a look at that. I just move down these 2 commands here, down to here. In fact, I'll delete the dot op, we're not going to need that one again. And we put in a dot lib for the minimum, that will go there, and a dot lib for the maximum. As before, hover over the dot lib, right click on the mouse, browse, select min, click OK, appears on the schematic. Same thing for the max, browse, select the max, click OK. Now, this is where it gets a bit tricky. How are we going to get those three different types of sets of transistor parameters into the transistor? Well, for one thing, we need to change the transistor from having just NMOS tip as its model to having the ability to pass a parameter in there. And the way that we do that is hover over NMOS tip and replace that. We use curly braces here because curly braces indicate to the simulator we're going to pass a parameter in here. We'll give this parameter the name of model, inspired. And so now what we need to do is step this model through these three different values which you'll see contained in here. We already are familiar with the model called NMOS tip, and you'll find a model for the NMOS transistor in this file called NMOS tip. If you look in this file, you'll see the model name has been changed to NMOS min, and if you look in this file, you'll see the model name has been changed to NMOS max, representing the min, the tip, and the max of the process. But the problem is, the command that we'd normally use for this type of function is called .step. That's a standard SPICE command. .step does not allow you to step text, or I should say alpha characters. It only allows you to step numeric characters. So we have to play a trick on the simulator, and what we do is we set a set of models, you could almost say fake models, which have numeric values. So we can go dot model is another SPICE directive, and that model name is 1. It'll become clear in a moment what we're doing here. AKO is a type of equate in LTspice. It stands for a kind of, and we're going to equate the number 1 with the minimum model process minimum process name NMOS min. Now you can actually enter the three of these just using the one box. So if I go Control Enter, I drop down to here and I can go dot model to a kind of NMOS tip. And as I said before, just think of AKO as equate. So 1 equates to NMOS min, 2 equates to NMOS tip, and 3 is going to equate to NMOS max. Place that on the schematic. And so finally all we have to do now is use the .step directive, standard SPICE directive, for a parameter called model, and step it through this list 1, 2, 3, and hopefully you'll start to see how all of this is going to work. So when the simulator starts up, the first thing it will do, it'll set this model here, which is a parameter into which values can be passed. Set that, give that a value of 1. Now 1 is equated to NMOS min, so what will happen is NMOS min will be substituted in here, and the simulation will run a DC sweep of VDS 0 to 4. So the next step, it'll substitute in 2, which is in fact NMOS tip. So NMOS tip will be swapped in there, and then finally NMOS max will be swapped in there. So we should get a family of curves representing the two corners of the process, the min and max values of V threshold and the typical. So let's see if we've got that all set up correctly. Yep, that seems to be working okay. So again, how do we know which one is which? We'll go up to Tools, Color Preferences, and the first trace, if you remember, was the minimum of the process, and that's green. So this is NMOS min. This one is NMOS tip, and this one here is NMOS max. You can check that out for yourselves. So useful here just to measure the slope of this line, say up here at 3.6 volts, measure the slope of this line at 3.6 volts and this one here at 3.6 volts, and just compare the three of them. So okay, we've carried out simulations for just standard variation of this voltage here on its own. We've carried out a simulation where the temperature is varying, and we've carried out a simulation where the process is actually sweeping from one corner of the process to the other corner of the process. So finally what we're going to do is look at device scaling, which is effectively the designer's ability to change the W and the L of the transistor and to see how the transistor behaves under those different transistor values W and L. So what we'll do is we can leave all of these in place, but we're going to get rid of the curly braces and just put back in a typical model there. So we're no longer parameter passing in here, and we're not stepping transistor models. This time we're going to be stepping the transistors scaling parameters W and L. So we're going to define a parameter here. Instead of model, we're going to define a parameter called S, which I just made up, and it's short for scaling factor. Actually, we call it SF, scaling factor. And that scaling factor will go from 1 to 2 to 20. It'll become a little bit more clear now in a moment. And then we hover over the W property there. We put in curly braces here. We put in our SF for scaling factor. We multiply that by 2 micron. And we do the same thing here for the L. Curly braces, SF for scaling factor, multiplied by 1 micron, curly braces. So what's going to happen is we're going to have 3 sets of curves. One where SF is 1, so we'll have a 2/1 micron transistor. The next curve where SF is 2, so we'll have a 4/2 transistor. And finally where SF is equal to 20, and then we will have a 40/20 transistor. So these 3 values here are going to be passed as parameters into these expressions here inside the curly brackets. So let's see how that looks like. Let's run. Oh, I think I forgot the list. Yes, I forgot the list command. So we've got we're going to step a parameter SF, and it's a list format. Okay, let's see how that works. Right, that's much better. So we can see here now, I can just tell you, you can go in here if you wish into the color preferences to determine which one is which, but this one here is the 2/1 transistor, in other words, the scaling factor equal to 1. This one here is the scaling factor equal to 2, and this one here is the scaling factor equal to 20. And you can clearly see as the transistor's length is getting bigger, the slope is getting smaller. In other words, the output resistance is increasing, or you could say the output conductance is decreasing. So what I'd like you to do, please, is to measure the output resistance at, say, 3.6 for this plot, and this plot here. So just in summary, we've looked at the effects of voltage, we've looked at the effects of temperature, we've looked at the effects of process variations, and finally we looked at the effect of changing the scaling properties of the transistor, in other words, the W/L ratio of the transistor. So that concludes the video.